Welcome to my course on quantum computing for the determined. My name is Michael Nielsen, and in this course I'm going to explain how quantum mechanics can be used to do all sorts of amazing information processing tasks, everything from quantum teleportation to quantum computation and fast quantum algorithms. To take the course, you don't need to have a background in quantum mechanics. I'm going to explain all the background that you need as we go along. What you will need, the main prerequisite, is determination and the willingness to persevere if you don't understand something the first time, to go back and take another look and try and understand it in more detail. What I'm going to do over the first few videos is explain in some detail the basic sort of abstract model of quantum computation. In particular, this is really kind of the foundation for everything that we're going to do later on in understanding fast quantum algorithms, and also things like quantum teleportation can be understood in these terms. And to understand the basic model of quantum computation, the main thing you need to know as background is linear algebra. In some sense, quantum computation, or at least sort of the abstract side of it, is really a type of applied linear algebra. So too is quantum mechanics. I am going to assume that you have some background in linear algebra. So things like vectors, for example, I'll assume you're very comfortable with, and matrices and ideas like matrix multiplication and matrix inversion and so on, as well as slightly more advanced concepts, things like, for example, Hermitian matrices, unitary matrices, and other similar sorts of notions. If you don't have this background, you can in principle take the course, but I think you'll find it tough going. You're going to need to look up a lot of different things. If you do need to get some more background before tackling the course, then I recommend the Khan Academy website, which has some very nice lectures on linear algebra, which can help you get familiar with the basic notions at this URL. There's one other thing that will help you cover the course materials, and that's some basic familiarity with and comfort with sort of notions from classical circuit theory. So conventional sort of logic gates, things like the AND gate, the OR gate, the NOT gate, and how these gates can be put together to do interesting logical operations. So you don't need to be super expert on them, but some basic familiarity and comfort will really help. Okay, so what we're going to do in this video in particular, the main thing, is to understand the qubit or quantum bit. And of course, when we think about information in the classical case, the conventional sort of case, we think of the bit as being the fundamental unit. So considered as an abstract entity, the bit is just, it's 0 or 1, and that's how we build up our computations in terms of manipulations of zeros and ones. And in terms of actual real, sort of the real physical world, we might represent a bit in terms of a voltage inside a computer, or maybe some kind of a magnetic domain on a hard disk, or it might be light in an optical fiber, or many other sort of possibilities. The qubit or quantum bit is the equivalent system in quantum mechanics. And to start with, as we sort of, in this very similar to the way we work with the abstract mathematical description of the bit, we're going to work with an abstract mathematical description of the qubit, and I'll explain what that is in just another minute or so. For sort of, the way you should think of it is that in some sense it's the simplest possible quantum system. So at least in the early part of the course, we're not going to be worrying too much about real-world realizations, but it's perhaps worth mentioning that the qubit can be realized in many different ways in the real world, just as the bit can be. So there are realizations of qubits in atoms, in photons, electrons, and many other different types of physical systems, some of them really quite exotic, in fact. But for our purposes, really the main fact is that it's the fundamental unit of quantum information. We're going to build up our computations by doing manipulations of qubits and of the states of qubits, and that's sort of, so we need to get a really good grasp of that. So, all right, let's get in and actually describe the details of the mathematical model. Not surprisingly, given the name, a qubit has two special states called 0 and 1, which basically they are the equivalents of the 0 and 1 state for a conventional classical bit. So this funny bracket notation just indicates that these are quantum states, and they're called, this notation is called the ket notation. So anything you see that has that bracket around it with any kind of label at all in there is an example of a ket. So the 0 is a label, the 1 is a label, and that's what a ket is. These particular quantum states are given a name, which is very important, and that name is the computational basis states. And so those computational basis states are going to turn out to have pretty much exactly the same properties as the properties of the conventional classical states of information, the 0 and the 1. So what actually is a quantum state? Well, I'm going to sort of give you a definition. The quantum state of a qubit is in fact a vector in a two-dimensional complex vector space. Alright, so that sounds very abstract and hard to understand, and I'm going to unpack it. First of all, let me just sort of draw in. These are, in fact, they'll turn out to be unit vectors. So here's sort of the origin over here. And so, of course, the screen is a plane. It's a two-dimensional real vector space, so it's not quite complex. But the way you should think about a general quantum state is that it can be formed from a linear combination of these two states. So a general quantum state can be written as a linear combination of the 0 and the 1 state. It's just a vector in a two-dimensional complex vector space. So in particular, in this case, if you just sort of eyeball it, well, alpha is about equal to 0.8. It's kind of most of the way along there. And beta is about, say, 0.6 over here. So that's the linear combination in that particular case. It's this quantum state here that I've drawn is a vector. It's actually got real coefficients, but in general, the coefficients could be complex numbers. So, this statement takes some unpacking. Why do we represent the states of a qubit as vectors in a complex vector space? In fact, why in a vector space at all? When we think about the bit, we represent the states of a bit in terms of numbers, 0 and 1. So why do we take this seemingly more complicated description? Well, I'm not going to try and explain that in full detail here. What we'll see over the next few videos is that it does let us build up a sort of a model of computation. So particular states which are near the 0 behave pretty much like the 0, and states near the 1 behave pretty much like the 1 state with a little bit of 0 mixed in. Why the complex numbers appear is also a subject in some sense of great mystery. It's worth keeping in mind that quantum mechanics was constructed over a period of about 25 years from 1900 to 1925. There are a whole bunch of Nobel Prizes won along the way. It's not an obvious kind of a theory. At the end of the day, this kind of vector here, that's a very simple mathematical object, and it'll actually turn out to be easy to understand the manipulations we do with it in the quantum computing model. But while it's simple mathematically, that doesn't necessarily mean that it's kind of intuitively obvious a priori why we should be using this. We will be able to build up some intuition as we look at the rules, and we'll quickly develop quite a bit of intuition. But for now, at least, you just need to accept that this is the way things work, and you'll quickly find that you actually become quite comfortable, particularly once we introduce quantum gates over the next few videos. Okay, a couple more notions, just sort of pieces of nomenclature that are widely used. I'm going to talk frequently about superpositions of quantum states, and this is just a fancy word for linear combination. So physicists or quantum mechanics tend to talk about superpositions of quantum states. So here's a superposition of the 0 and the 1 state, meaning just a linear combination. And another useful term is the term amplitude. So the amplitude, alpha is an amplitude here, it just means it's the coefficient. So the coefficient for 0 in this state is alpha, and the coefficient, and the amplitude for the 1 state is beta. Very simple, and a useful term. So I said before that the quantum state of a qubit is a vector in a two-dimensional complex vector space. Actually, it can't be any old vector. There's a constraint which is imposed, and the constraint is just that those amplitudes, the sum of the squares of their absolute values, must be equal to 1. And this is often called the normalization constraint. And the reason why it's called that, well, if you think of the state 0 and the state 1 as being orthonormal vectors, then this is just the constraint that the length of the state vector be equal to 1. So it's a unit vector or a normalized vector, and that's why this is called the normalization constraint. So in general, we can sort of think of the state of a qubit as just being a normalized unit vector in this two-dimensional complex vector space. And if there's one sentence you're going to take away from this video, that should be it. The quantum state of a qubit is a vector of unit length in a two-dimensional complex vector space. Okay, so alright, we've pretty much covered everything we need to know about qubits. There's one final point I want to make. It's a point that can sometimes cause confusion. It's tempting to look at this computational basis state, the 0 state, and think, oh, that must be the 0 vector in the vector space. No, that's not right at all. The vector, the 0 vector, is over here at the origin. It's sort of an unfortunate piece of notational overlap that this looks like the 0 vector, but it's not at all. It's a vector of length 1, the computational basis state 0. In practice, this doesn't cause any confusion, but it's something worth being clear about from the outset. Okay, so let me come back again to this question. We're going to come back to several times, in fact, in the next few videos. This question of what exactly does this quantum state mean? How should we interpret it? How should we understand it? And it's tempting, or many people find it somehow convincing, to say that somehow what this state is it's simultaneously in the 0 state and the 1 state. And when people say this, I must admit, I don't really understand what they mean. It seems to me that what they're doing when they give this kind of explanation is they're trying to impose their classical prejudices on the quantum world. And, maybe that works for them, but I can't really make much sense of it. The strategy we're going to take in this course is instead to start with sort of the basic mathematical description, and then start to look at some of the consequences of it and build up an intuition in that way. Okay, alright, so that finishes this video. In the next video, what we're going to do is just look at a few sort of general ways of working with the qubits and the quantum state of a qubit. We're just going to try and get a little bit more comfortable.